Section 15.8, substitution and multiple integrals. So some learning goals here. You should be able to understand maps, be able to find them, especially the special case of linear maps. Be able to calculate and apply Jacobians, that's something related to these maps. And then know how to use a general substitution formula for multiple integrals. By the way, just one little disclaimer before I get into this video and the entire set of videos for this section. There's two terms I'm going to use somewhat interchangeably. So sometimes I will talk about substitution, sometimes I will talk about change of variables. And I'm just going to use those two terms somewhat interchangeably. They both are suggestive in different ways. They change of variables is you'll see as we do this, we are going to be literally changing sets of variables from one to the other. Substitution is going to be very akin to the substitution method that we learned at the end of Calc 1, start of Calc 2 for evaluating integrals. They're both suggestive. I'm going to use them pretty interchangeably. Okay, so to get into our discussion here, I want to ask the following question, which is consider the following integral. X runs from 0 to 3. Integrate the square root of x squared plus 4 times 2x dx. How to do this? Okay, this is going to be, this is a pretty easy, straightforward, substitution problem. So first off, observe here that, how to find the antiderivative of square root of x squared plus 4 plus times 2x dx. It might take a little bit of thought to find an antiderivative for this function. And you certainly can do it, but it might take a little bit of thought here. But the easiest way for us to do it is to say u is equal to x squared plus 4, du is equal to 2x dx. And so then this integral is going to, we're going to replace it with, okay, so let's see here. This becomes du here, and then we just have square root of u, and when x is equal to 0, I'm just going to write down u of 0 here. When x is equal to 3, u of 3 here. So observe what happens going between these for substitution. Obviously, it's not too difficult to evaluate this. So this is u from 4 to 13, square root u du. Easy to evaluate. The substitution here, we are going to change x to u and change dx to du, and we have to be careful about how we're doing it. We're not just literally replacing x as we use. There's rules that we have to follow on how to replace, dx with du, and like this way here. And the goal is we are now integrating with respect to u. And the goal should be that this should be easier to integrate. Let me just point out here, we have the idea of number lines here in terms of u and x here. So somehow the interval u runs from 4 to 13. Somehow this corresponds to the interval x runs from 0 to 3. Under this function, this function ties together these two intervals right here. Okay, so this is all, revisiting pretty easy end of Calc 1, start of Calc 2 stuff. Okay, so now I want to kick this up to double integrals. And to do that, I'm going to do a polar coordinates example. So once again, I'm going to say how to evaluate the following integral. The double integral over d of square root of x squared plus y squared dx dy, where d is the integral, d is the region. I'm going to make it this macaroni-shaped region right here. Okay, so this is in the xy plane. Okay, this looks like a perfect candidate. This looks like a perfect candidate to use polar coordinates here. What are the bounds on theta and r? Okay, theta runs from 0 to pi. R runs from 1 to 3. And so we know that this is going to equal the integral theta runs from 0 to pi, r runs from 1 to 3 of, we have to do substitution here. We know that x squared plus y squared, that's r, times r dr d theta. And so let me draw a picture that I haven't drawn this kind of picture before. I'm going to draw something in the r theta plane. I'm going to draw something in the r theta plane. So let's see here. R is between 1 and 3. Theta is between 0 and pi. So the region that we're integrating over in the r theta plane is going to be this rectangle. And so let's observe here that we have some kind of substitution going on here. That we are going to change x and y to r and theta. And we're going to make this easier to integrate. Primarily because, I guess there's two reasons that we're making it easier to integrate. One is that the integrand is a lot easier. Square root x squared plus y squared. That's nasty. R times r. Okay, r squared. It's hard to come up with a significantly easier integrand than this right here. Second thing, the region that we're integrating over is a lot nicer. If we try to do this, we'd probably have to chop into like 1, 2, 3 sections or so. If we're integrating it, slicing it vertically. Here, we're integrating over a rectangle in the r theta plane. Can't ask for anything nicer than that. The final thing that I want to point out here that's a parallel between this and this example is that in both of these examples, there's like extra factors that get thrown in when we change between like du and dx and dx dy and r dr d theta. So right here we have the fact that du is equal to 2x dx. So there is a factor of 2x that gets deleted going from here to here, or as you can think of going from here to here, there's a factor that gets 2x that goes thrown in going from here to here. And then in this example, dx dy is equal to r dr d theta. There's an extra factor r that gets thrown in here. And so we should be developing this general picture of substitution here, where we're going to change variables. And, remember I just kind of said I'm going to be using substitution, change of variables, somewhat interchangeably. We're going to be changing variables to make the integrand easier to find an antiderivative of, to make the region that we're integrating over a lot simpler. And when we do this, there will be factors that we'll have to throw in and stuff like that. So throwing in this factor r. So that's an introduction. I think that's a good introduction to what's going on in the section 15.8. We actually haven't really got into stuff yet, so in the next video we'll start developing the machinery that we'll need in order to come up with the general formulas that we want to in this section.